Good morning, guys. Sir DV is here again. So we will be continuing our lecture from the conceptual discussion last time. We move forward to some formula to consider when we deal with the nominal stresses concerning bolt failure. So we recall some simple stress concepts on shear tension and bearing. So this is actually an application of the simple stress formula P over A, wherein the only difference will actually be noted on the area determination. For shear, the area to be considered is actually uh, the shear plane area. Okay, so when you say shear plane area, we are referring to the bolt. The bolt, if the lap splice is the one to be considered here. Okay, so your shear plane is this one in between. Okay, so this plane here is actually the shear plane upon which your bolt connecting the two plates will be divided, no, by the shear plane. Hence, the area considered on the bolt is simply this area AB. Okay, so the number of shear plane in this case is 1. So this is 1 times the area of the bolt. Okay, so this is the area of the bolt. So for tension, it's different. So we have say a T-section connection, okay, wherein a plate is holding. Okay, so this is now so the plate is holding the T-section, and you have here a bolt. Okay, so the area again of this bolt is simply the area of a circle multiplied by in this case we are considering only the tension per bolt. Okay, so there's no need to multiply it with that of the number of shear plane. Okay, so even though this is only a single shear plane here, this is the shear plane that I'm talking about, since the force of tension is actually not along the shear plane, so we consider only T here to be applied per bolt. So you simply have to divide your P here will be equal to T divided by the number of bolts. Okay, it's not the number of shear plane, but rather the number of bolts. Okay, so we are now considering a per bolt pattern here, considering also here, of course, your T. If this is a concentric connection, your P here will simply equal to T divided by the number of bolts. So for bearing, same case, but this time your bolt failure will be uh, the size. We have two plates again. So this is your bolt. So the bearing of this uh, pressure applied on that bolt will simply be equal to the thickness of the bolt times the diameter, okay, of the bolt. So it's a dt. So the area considered here is simply the projection of the bolt diameter projection of the bolt diameter to the plate, which is defined in terms of its to the plate thickness. Okay, so those are simple stress formula. Just recall your basic strength of materials on it. So we also have the tensile strength of bolts in terms of the LRFD condition. You'll be using a phi equivalent to 0.75 as your reduction factor, considering this as your LRFD reduction factor. So the nominal strength is simply equivalent to the ultimate tensile strength of your bolt multiplied by the area of the bolt. Okay, so this is now the net tensile area, okay, which is 0.75 of your AB. Okay, so it's a 75% efficiency on the area of the bolt. So the reason for that is because the uh, consideration of your thread. Okay, so that's why you cannot use the full area of the diameter of the bolt, since there are some reduction on the caused by the threaded part. So this equation can be reduced into FNT-AB, where FNT is simply 0.75 of FUB. So the 0.75 here can actually be placed on the FUB as a coefficient, and therefore using a nominal tensile strength equivalent, or a net, rather a net tensile strength equivalent to 0.75 of FUB. So for the shear strength, we are using a 0.62 FUB on the basis of your von Mises criteria. Okay, so which is actually 0.558. Okay, but since this shear strength has something to do also with the bending strength, we use this tau and FB in between 0.66. So in between 0.66 is around 0.62. So we are midway the value of the von Mises shear criterion and the bending allowable bending coefficient of steel material, which is 0.66 of your FU. Okay, so we have here a 0.62 as FUB as the basis of your shear strength. M is the number of shear planes. AB is simply the gross area of the bolt. Okay, so why is it that this was referred to the gross area, not the net area above? Because usually your threads are not within the range upon which your shear plane is located. Okay, so that's why you use the area gross instead of the net area here, okay, which is 0.75 AB. So equation 9.4.2 will now be written in terms of a simple 0.62 FUV equivalent to FNV. Okay, so again, this is an FNV. It's a nominal resistance for shear, where FNT here is a nominal resistance for tension. Applying a correction factor of 80% to account for the connection length. Okay, so we now multiply this by 80%, you get a 0.50. So ganun nakuha yung 0.50. FUB MAB. Okay, if you are using the FUB term, but if you are using an FNB term, you will be simply multiplying by 0.80 FNB MAB. Okay, so this is when the threads are excluded from the shear planes. That is actually on the basis of AB, the gross area of the bolt. When the threads are included on the shear planes, meaning to say there are threads crossed by the failure path of shear, then you again reduce this 0.50 to 0.40 to account for the thread inclusion. So X bolts, no? So these are excluded thread, included threads. So for the bearing strength of the bolts, wherein phi is 0.75, we make use again of the shear strength of the plate, tau UP, as 0.62 of FUP without length correction factor. So the length, the LC now is the distance along the line of the force from the edge of the connected part to the edge of the hole. Okay, so where D is the diameter of the hole, so there's no W here. No? So correction. And alpha is simply the tearing angle. But the minimum tearing angle actually is 0. No? So this is the shortest distance upon which your plate shear failure or block shear failure of the plate is to be considered. So note that alpha is 0 as a lower bound of such failure. And therefore, your nominal resistance now becomes simply the shear area multiplied by tau UP, which is 2LC times T multiplied by 0.62 FUP. So 2LCT is 2 times this length here. Okay, so this is considered one LC there and another LC here. So this is 2LC multiplied by the thickness, and 0.62 FUB is the shear rupture strength of your plate material. So it is recommended to use center-to-center spacing with S is equal to 3 bolt diameters, subtracting 1/2 bolt diameter to obtain the center-to-edge spacing. LC may be taken equal to 2.5 bolt diameter. Okay, so this is the rule of thumb. Now, if you have 2 holes here, your center-to-center spacing S is always 3 times the bolt diameter. Okay, so if this is now a center to edge, okay, it's the edge of the plate. So we simply deduct 1/2 bolt diameter there from a 3 bolt diameter. So this is spacing now S prime is simply equivalent to 2.5 dB. Okay. So if we do that, our Rn now becomes 2 times 2.5 dt multiplied by 0.60 FUP. So this is approximately 3.1 FUP. Again, a basis for LRFD equation. So for the design bearing strength to prevent hole elongation exceeding 0.25 inch, these are now the cases. No? For case 1, uh, usual conditions. All holes except long slatted holes perpendicular to the line of force where the end distance L is at least 1.5 times the bolt diameter, center to center spacing at least 3D, and there are 2 or more bolts in the line of force. Okay. Okay, so this is now, I think this is the 3D of the bolt, no? Okay, so this is VRN 1.2 LC, T multiplied by TFU less than or equal to this limit. So these are limiting value for such a resistance. It cannot exceed this 2.4, double of what is this one here, no? So this FUT times D, okay? Not double because this is dt and this is 1.2 LC. Relating it to D is not equal. Okay, so the basis of this formula is actually this formula here. You will take note that this is the basis of the LRFD equation, and to give enough factor of safety, we cannot exceed this 3.1 here. So here we have only 1.2 as your maximum resistance PRN. And for long slatted holes, this is reduced to 1.0, even smaller. For nearest edge, about nearest the edge, this is reduced further to 0.75. And when there's hole elongation exceeding 0.25, okay, so in case this exceeds 0.25 and hole ovalization is tolerated, meaning to say that slip critical is not considered. Okay, these are bearing connections. Then this is bigger than this one, but still less than 3.1, the basis of the LRFD equation. Okay,